I'm Rajesh Ranganath. I'm at NYU, and I'm going to tell you about some things in generative models. Looking at some of the titles this time, I saw like folks that I think Shamli maybe is telling us something also about generative models, and I was like, the world has maybe changed, so hopefully you'll get something from this. So starting from scratch, a generative model is really a way to take some like randomness that your computer knows how to generate, like sampling a Gaussian or sampling coin flips, and then converting that into like a sample from some structured distribution that you want. In this case, like, here's what your computer produces, this is what a generative model is, and we get samples, and these are photos of my old student, Mukund Sudarshan, who actually attended CGSI. So it turns unstructured noise into structured samples. And there are two broad classes of this. Ones are autoregressive language models, and the other are corruption-based generative models like flows and diffusions. Autoregressive models are like super simple. They basically take a probability distribution and they factorize it in the way that you'd see in a textbook. It would be like, if I have like 3 elements and I want to know what the distribution of that is, I'm going to model that as the distribution of the first element, the second element given the first element, the third given the first 2. And this is like a decomposition you'd find in a textbook. What's cool is that to like actually build a model here, you want to make some parameters, and the parameters are going to be shared. That's typically done with a transformer. There are other approaches like state space models. Even also training here is something that you'd find in like an ancient textbook. Like if you look up like Chris Bishop's original book, which is about 20 years old now, you'd learn about maximum likelihood. And the way that people train these models, or at least do the first pre-training step, is just with maximum likelihood. You like take a big collection of data, and here big is really big. You're going to say like compute the log likelihood, and then just try to maximize it with stochastic gradients. And there's a lot of work here. Even though that like sort of the base technology is like what you'd find, making it work is challenging. So like memory requirements, compute requirements with GPUs, communication across them, even getting gradient-based minimization to work. There are learning rates. There's also things about like how to parameterize things to make scale work. Like a big name of the game is like, you may be only able to train like the biggest model once or twice. How do you get evidence on how to train that big model based on smaller trainings? And so making that connection tighter, there's some interesting math behind that. And then also, of course, curating the right data. That matters as well, too. It's used for lots, like language models, reasoning models, which are like souped up language models with extra compute steps. They're also amino acid protein models. For the other class, they're diffusion models. People might be less familiar with them because they're like touchless, except maybe images a little bit less, but they're also everywhere. Probably the first big thing for a generative model was the stable diffusion converting text into images. I think that was earlier in 2022, but people also use these for proteins, molecules, 3D structures, and then they get good likelihoods as well too. If you think about the generative model literature before diffusions, it's kind of fragmented. Some people are like, hey, you want this for like good scores, you want this for good generations, but at this point, like it all coalesced, and they're like, hey, this thing is actually better at both. So what is a diffusion model? This picture kind of summarizes it to you at a super high level. You define some process by which you take an image and you convert it into noise that the computer knows how to make. In this case, it would be standard Gaussian noise. And the learning problem is really just how to learn to reverse this, where you're learning to reverse it in small increments. Like the model ideally takes this noise and makes something that's like a little bit of a fuzzy cat, makes it a sharper cat, and then finally like a cat that like looks like something that you want. Mathematically, diffusion models have a little bit more complexity behind them. The continuous version of them requires like a stochastic differential equation. But in your head, you can think about it as pictorially the same thing, where you define some stochastic differential equation that corrupts your data, and your generative model is the stochastic differential equation that you're learning to reverse it. And you can train these things with maximum likelihood as well. That principle is one and the same. Doing this really requires like solving a stochastic differential equation, or integrating a stochastic differential equation, or solving a PDE, which is the Fokker-Planck equation. It's intractable here, and so you'd need to do something like variational inference. Variational inference, again, is like a textbook idea. You'd find it in the Bishop book from 20 years ago, where if you have some log probability you're trying to compute, you're going to go through a couple of steps. First step is like average out over the stuff you don't know. So in this case, they're the hidden paths of the SCE. You do change of measure, which is like multiplying by 1. So you're like multiply and divide by this q. And then use Jensen's inequality, which is a lower bound. The challenge here is that like you don't know these distributions explicitly, but like if you actually just read a stochastic analysis book, you can carry out these same steps just with a little bit more complicated technology, where writing down the marginal distribution is done with the Fokker-Planck equation. Writing down the actual like expectation you do with this Feynman-Katz formula, and then change of measure and Jensen's inequality works the same way. So like that was sort of like warm up on like what these models are, just to see like, you know, hey, there are two classes of them. You can train them in a similar way with maximum likelihood. Diffusion models have a little bit more math, but like we can talk about like how they're used. So this is a real example that I just typed into Gemini. I was like, you know, if the capital of Spain becomes Paris, what would the capital of France be? It's kind of a reasonable answer. It's like, hey, this is a little bit of a trick question. It's like, you're not telling me it's aligned. I was like, yeah, it's interesting. But the feeling that you should get is really like the way you use these things are like queries followed by answers. The queries might be like not like text queries. It could be like, give me a molecule that binds to this antibody, but they're still like queries which are some conditioning set and some answers that get produced. Here's another version of that where you know, we're taking stable diffusion, which is a text-to-image model. We're passing in some prompts, which are like a photo of a black motorbike and a yellow bird is what you want. Doesn't really look like a black motorbike. We could then say a photo of an orange cow with a purple sandwich. Got like a purple background, a normal cow. Photo of a brown knife and a blue donut. You're like, oh, you know, these images, they kind of look okay, but if you're really like trying to like match them to the text that's there, you'll be like, this looks odd. You're like, you know, hey, it doesn't actually produce the things that I want. And so what do you do? Right? Really like, you know, I give you that technology of like, hey, we can like take some data, we can like maximize its likelihood, and you can be like, you know, get something. But then when you get results like this, what do? Do you go out and you're like, let me collect more data and then train a different model? Do I like build a bigger model? It feels like kind of like really strange on when you're thinking about what this question is. But we can try to like make the goal a little bit more formal in some way. The goal really here, like from like a math standpoint, is like you want to produce samples that have high scores. So you have some context here. These contexts are like the text that I put in, and the X's are the images that you get out. And you want to get things that have like high scores. You could then say like, what's the point of a generative model? Right? Because like I have this scoring function, maybe what I'm trying to do is actually just like maximize over this scoring function and just find like for the specific like query that I put in this context, find the X that gives me high score. This optimization is non-trivial. If I have like a sequence of text, I have to optimize over this discrete object. It's not easy. The second is like these rewards are actually coming from data, so they have errors inside of them. And maybe the third part, and I think it's the most important one, is really hard to pre-specify all the properties that you care about. Like if I'm like, oh yeah, I just want the count of the objects to match like the number of the objects that actually appear in the image. That's one facet of it. Maybe I want the colors to match. Maybe I want them to be nice and rounded. It's really hard to just predefine all of those things. So instead, like, you know, what people do is they're going to say like, I have some generative model that captures some of the stuff. Like this is not bad, right? The cow looks like a cow. But like some of the facts about like, you know, I want an orange cow are wrong. Maybe I can like tilt it or steer it towards samples that look better. So people set up this target that's at the bottom where they're like, take my original generative model. And when you have your original generative model, I want to like bend it towards places where the rewards are bigger. So this is saying like, hey, my original generative model, multiply it by this like exponential of rewards, and then try to sample from this distribution. So like I'm saying a lot about classical textbooks here because like, you know, that's actually a really like classical problem where like the goal is to sample from an unnormalized distribution, and this thing appears everywhere in like like really old machine learning stuff. An example is like if you want to sample from a posterior distribution, the posterior distribution is proportional to the joint. And so you know it up to a normalization constant. That's what this equation is here. So then you could open up your, the Bishop textbook or a later one and be like, hey, what did people tell me on how to sample from these distributions? They'd be like, use Markov chain Monte Carlo. I could use sequential Monte Carlo, variational inference, combinations of them. Kind of like what's interesting about the setup is we took like, hey, here's a generative model, here's a scoring function, and we defined a problem that led us to a bunch of algorithms that exist in the literature already. And we're going to look at one of them. We're going to look at sequential Monte Carlo for diffusions. So the way that diffusion sampling works, it's that like picture of the cat you should keep in your head. The picture of the cat that you should keep in your head is you start from noise, you go from a cat that's a little bit less noise, a little bit less noise, and then finally something that looks like a cat. This is sampling from like a sequence of probability distributions, each with less noise in the image. Sequential Monte Carlo, it looks complicated, but sequential Monte Carlo is an algorithm to sample from a sequence of probability distributions or measures. And the way that sequential Monte Carlo works is like, you're like, okay, given that I've sampled up to like the certain point, let me guess a particular value, and let me score that particular guess relative to the thing that you're trying to target. And that's what this formula is right here. This formula is, in the top is the thing that you're trying to target, and the bottom is what you started with your guess. So it's what you had in the previous time step times this proposal, which is extending your guess. And this ratio just gives you the score of like, is this good or not? And then the way the last step of sequential Monte Carlo is just to sample based on the normalized values of these scores. And so you can see the connection. The connection really is that sequential Monte Carlo is sampling from a sequence of measures. Sampling a diffusion model is also sampling from a sequence of measures at different noise levels. And so you can just actually use sequential Monte Carlo to sample from diffusion models. And there's some examples of this to do like conditional sampling. Say I want to produce like an image of a cat. And we kind of wanted to just see like what else is really possible. To really figure out what else is possible here is we're going to set up a sequence of measures here. So these are just probability distributions across like the different noise levels. And the way that we're going to do them is we're going to start from our original model, and we're going to just multiply it by some function. This function is not really specified. The only thing that you care about for this function is that when you finish the generation, you're going to meet the distribution of interest, which is the original model pushed towards these scores that are higher. And so there are many choices that satisfy this product, but like, is there intuition on how you'd pick them? It turns out like two things can really help you figure this out. One thing that will help you figure this out is that sequential Monte Carlo picks things that have higher probability, or where the score is really higher. And so what we kind of want to do is we kind of want to set the probability of these intermediate steps so that the final generation will have good value. And intuitively, you're like, okay, how might I do that? If I could take my generation, so I could take this like partially noised image, and if I could predict what the score would be if I complete the generation, then that prediction should help me be like, should I continue on this generation or should I throw this away? And then that's really the idea of like what happens inside these algorithms. It's like pictorially depicted here. Here the scores are increasing vertically, and like maybe you start with these like 4 image generations, and then you're like, hey, if I take this bottom one, and then I like predict its score, it's going to be too low. I don't want to keep it. And like this is kind of pictorially what's happening inside of sampling algorithms. And these reward predictions we'll call intermediate rewards. And there are lots of ways to build them. You could just say, take a diffusion model. It'll one step produce like a inaccurate version of what the data should look like. And you can just say, give me the score of that. You could also train a regression model that uses the sort of like noise process in a diffusion to say, hey, I know what like real data looks like. I know what like noisy data looks like because I can just manually noise it. And I'm just going to try to predict what the score is from that noisy data on the real one. And this is a regression problem that I've written down here. In terms of choosing potentials, again, you have lots of choices. One you could say is like, I want to prefer particles that have increasing rewards. Another one is like, I want to prefer things that have like high maximum value. Increasing rewards are generally a good idea. If you have a bounded reward, though, increasing rewards may be bad because if you hit like the maximum score, you might say, I can't increase it anymore, and you'll remove things that are already pretty good. And this leads to this algorithm called FK steering, where FK steering is really just a couple of steps. First thing you're going to do is you want to sample from a generative model that tilts towards things that have higher score. And the way you're going to do that is you're going to pick these intermediate rewards. So you're going to try to figure out how to take the generations you have and see like, hey, what would the reward be if I completed the generation? We're going to pick these potential functions so we match the time zero distribution. And we need some proposal for use inside of sequential Monte Carlo. And so here are some results from doing this. The algorithm is relatively simple in that here we have a reward model, which is image reward. It just scores images for conditional generation. The proposal is the model. The intermediate rewards are just come from one-step denoising, so you don't need to train anything. And the potential is the maximum value. And the plot you should look at first is the one on the right, where the x-axis is computation and the y-axis is score. So like if you're higher up, it's better. It's a different image generation score called GenEval. And you can see some fun things where if you take like Stable Diffusion 2, which is a smaller model than Stable Diffusion XL, for less computation, so this point right here, you can get a much better score than you can with the bigger model. And so like, putting this together is a lot of stuff. If we take one of those like probabilistic sampling algorithms, adapt them to a smaller model, we can get better performance than you can get with a larger model. And those examples I showed you earlier are actually just examples of things that you could correct with these kinds of steering algorithms. Like the original base models are pretty good, but they're just like a little bit off. And so if you can like filter them the right way, you'll get stuff that more closely matches your prompt. Like here your cow is orange, and here your donut is blue sprinkles with a brown knife. And you can use these same ideas for language modeling as well too. Here we took a continuous diffusion language model and tilted it towards like language acceptability scores, and we can see that they like improve a ton. You can also tilt them towards like perplexities as well too. The example that I really like is toxicity, where you can take a base language model that's not very toxic. The toxicity here is like 0.3%. A held out toxicity classifier. So there are two toxicity classifiers, one that you might use for building your model, one that you'll use to evaluate would say 1.9%. Even if you sample from these models like 8 times and then said, well, give me the most toxic one, it's still going to be only 10% toxic. But if you use these like steering algorithms, you can get up to like 50% toxicity from these generations. So like if you're familiar with sequential Monte Carlo, maybe you wouldn't be surprised because it is used for sampling rare events. And in your head, you should be like good stuff, maybe a rare event. In this case, toxic generations, bad stuff is a rare event, but we can like push our models towards it. And even though this stuff is relatively new, people have already adapted it for looking at 3D structure of complexes. There's a model that's built out of MIT along with some companies known as bolts, and then they do something called bolt steering, which is based on our FK steering, which is just steering the generations towards things that match physical properties that are known, like chirality. I think there are 5 or 6 other ones. And you can really kind of see the same kind of thing happening here, where you should be comparing the blue to the green. So the blue is like when you do this kind of steering, the green is when you don't. We can see on like all the other evaluations, blue and green are about the same. So they look similar. But if you want to look at physical validity, steering towards things that are based on like physical knowledge of what these structures should look like really improves physical validity. And so your takeaways for this part should really be like, when you see a generative model, there's some sampling process that underlies it. And these sampling questions have been things that have been studied in machine learning for probabilistic inference, in statistics, and in physics. If we just adapt those algorithms, you can get like improved performance like we saw in that physical binding case, but you can also get it with less compute like we saw in the text-to-image modeling. So the next thing I'm going to talk about is like where do these rewards come from? Some rewards, as we saw, came from physical knowledge. Some other of them could come from like, is the math correct? Maybe I'm executing some code and seeing, did the code produce the result that I want? But a lot of it comes from like human ratings. Like, is this generation good or is this not good? And then that's where the idea of preference data comes in. So in preference data, we collect 2 generations based on a particular input. So here the context for this like healthcare example is what is ivermectin? And there are 2 generations. One generation is it's like a special bug spray or worm medicine for your body. It's a relatively accurate description. Another one is a macrolytic lactone anthelmintic. I'm not going to read the rest because I don't think I can read the rest. But it's like a much more technical generation. And so like what preference data is, you show these things to people and then you're like, hey, is generation 1 better than generation 2? That's the question you ask them. And this is a step in training of a lot of large models. Like the first step that you get is like take a big collection of data and maximize the likelihood. But if you were to just say like take a language model and then do that on internet scale data, you get something that looks like autocomplete. It's not something that's like interactive, being like, hey, here's some text I can put in and I'll get an answer back out. Because really it will be like, let me find where that text existed on the internet and try to finish the words based on what that looked like. And so then there are a bunch of things that are done post-training, like instruction tuning, just getting it to follow instructions, preference learning, alignment, reasoning is a big thing you'll hear about. And so I'm going to tell you a little bit about preference learning now. So there's a ton of papers in this space. Like if I were to have my student push this plot to 2025, it would go up even further. There's lots of research, and there are like a ton of methods. And like the question really I have when I see like all these methods that are there is like, how do we attempt to understand them? Like what's the underlying principle here that will sort of we can ground to look at what these methods will do? And the standard setup for like non-preference data is a little bit easy to follow. You get data from a distribution and you want to mimic that distribution. And so the way that you'd formalize that is you'd write down some kind of like distance or divergence between the 2 distributions and you're like, let me minimize this. And then maximum likelihood is minimizing the KL divergence, and it's just an example of that. And so like a learning principle in your head is just like, I just want to make my model look more like my data. But when you have preference data, you don't actually see what you want. You just see like whether one sample is preferred over another. You don't see like, hey, this is the thing I want, and I can go ahead and maximize its likelihood. And so you really need something else. And the way that we're going to try to understand this is by looking at what the preference sampling distribution is. So the preference sampling distribution would be, you get to see queries, you get to see sample from one generator, you get to see samples from another generator, and then you get to see the preference. So like I show a person, you know, the 2 generations, I show them the context, like what is ivermectin, and then the 2 generations we saw earlier, and I ask them, do you like this or do you not? And that's sampling L equals 1 means they liked Y1, L equals 0 means they like Y0. And any goal that we have for an evaluation should be defined with respect to this distribution. So our question is like, what is the right goal? What score should we use? It's not obvious. Well, we can write down some desiderata. One desiderata that you might want is like you want to actually respect the preferences. Meaning that if you have like a really simple setup where there's only a single query, just like the ivermectin query, and then each generative model only produces a single generation, like the 2 things that we saw, the one that's like for little kids and the one that's like, you know, if you have like a super PhD in developing ivermectin. And then like what we really want is like, you know, in that simple case where everything is like a single object, then we want to actually respect the underlying preferences. Meaning like the evaluation should just be like, hey, whether you're going to score something as good or not will be just what the actual preference classifier says on Y1 versus Y0. So like if Y1 is preferred by this preference, meaning the probability of it being selected as yes is very high, we want our score to be very high. If you don't satisfy this, then like different generations get evaluated differently, or you don't really respect the preference classifier. The other thing that you want is you want to respect prevalences. There's a lot of math on this slide, but roughly it's like if I have like 2 different things in my like query distribution, and there's a probability of half on one, half on the other, then I'd want my score to sort of split across that. Like I want half the score for query 1 and half the score for query 2. And this is what it looks like pictorially. If I have like, you know, some query that just puts all its distribution on on query x, and then another one that puts all its weight on query x prime. If I build a new distribution that is a combination of the two, then the score should be a combination of those two scores. And if you don't satisfy this, you're not going to respect the underlying distribution of the chosen queries or the generations, meaning that you'll be like, even though my generative model is going to say this kind of generation with probability 0.5, I'm actually going to put like a 0.3 in front of it. It feels like a weird thing to do, and that's why we're writing it as a desiderata. And even though those two properties feel like relatively innocuous, they close the gap really quickly, meaning that like informally you can say that if you want to satisfy both of those properties, the only thing you really need is win rate, where win rate is just between two models is the expected score that y1 is better than y0 passed through this function that you can think about as like a increasing function. And so from this, you should really get like all methods should be understood through win rate. And there are just like win rate maximization methods. So direct win rate optimization would be this algorithm called reinforcement learning with human feedback, which just maximizes the win rate subject to this KL divergence. There are also two-player games people have set up. This is out of DeepMind. There are many, many games. They set up a zero-sum game, but you could actually construct other ones, where in your head this game is like one of the generators is trying to win, the other generator is trying to win. You're then just saying both of them try to win more, and then you're going to take the resulting solution. And there's a bunch of nice properties you get. Like if you want to really boil it down, why do you care about win rate? Well, we said that if you want to respect those two properties of prevalence and preference, you'll get win rate. And if we maximize win rate directly, then like you don't have to think much. Making the objective higher means win rate is higher. If you maximize it all the way, you'll get like the solution that wins the most. And this maybe feels like the end of the story, but if you know more about this literature, you'll be like, hey, there are a bunch more algorithms here. Why are they here? It's the question you should have in your head. One of the algorithms is direct preference optimization, which is a fun algorithm made by folks at Stanford. Roughly, there's like two optimization problems that happens inside of like preference learning. One, you have to take data that looks like 1 was preferred over 0 and learn the preference classifier, then do an optimization over it. Direct preference optimization realizes that you can collapse those two optimization problems into a single one, which is training this classifier. And it's nice, only one model is required. So you'd be like, maybe that's the reason that you want to do this. But like we could actually just look at this direct preference optimization through this like lens of win rate. One, like direct preference optimization uses offline data, so meaning that we take some data sampled from some other distribution. And you can see funny stuff, like if you have like dog is better than cat, which is better than hippo, if the underlying data that only sees dog versus cat, you could shift most of the probability to hippo, even though it's least preferred, but still score really well under this loss. There are like maybe like 5 or 6 papers that are written on that subject, which are interesting. Then you could say I could go the online version. So the like offline data means like I collected data under some distribution. Online really means like I'm going to collect it under the generative model that I'm interested in. And you can see here from this plot that like, there is some relationship, and maybe like somebody could prove some math about the relationship between the DPO loss and win rate. But you can see things that like, maybe you're here and your win rate is really good, but your DPO loss is not so good. And you could shift like all the way down here. And your loss for DPO goes down, but your win rate also goes down. So meaning like there's not like a direct correspondence between the two. And there's not even a regularized correspondence, so you can actually set up things where you make the loss actually go down, but the win rate is worse, and it's actually further from some reference model that you want. The last algorithm that you could see if you're like really pulling into this literature is supervised fine-tuning. It's really like the most straightforward one. It's like, okay, I don't know exactly what is the thing that I want, but I'm not going to worry about this problem. I'm just going to take the one that's preferred. So if I get to see 2 generations and one of them is preferred, I'm just going to maximize the likelihood of the thing that's preferred. This algorithm doesn't really respect prevalences or preferences. If you want to get an idea on it, imagine that your model places all its probability on the thing that's the best. And that's a good model, and you should be like happy with it. But like if your data is collected under some distribution where you sample things that are not as good, meaning that they win with a really small percentage, if they still win, the overall score of this is just going to be infinite. But what's interesting about supervised fine-tuning is you can actually improve the win rate. Like you can mathematically write it down, and you can show that like it depends on the variability of the initial model. You can actually write down math that says if I filter my data so that it correlates with winning, then the overall improvement will be higher. So you might be like, why did I tell you about all of that? You could be like, hey, I told you that win rate optimization is what you want. And then there are algorithms that are like you start from, like reinforcement learning with human feedback, which do win rate optimization in a regularized way. And so why is there direct preference optimization? Why is there supervised fine-tuning? Well, in theory is what you'd expect here, that just maximizing win rate's best. On the right is what you observe if you do this in practice. Like the direct preference optimization will be better, and sometimes supervised fine-tuning is even better. So you're like, why? I did tell you that this requires estimation of two models, and so maybe it's actually like having these two models that's the problem. So we can give extra information. So we'll give like the true ground truth preferences classifier to this model. And that does even worse. So like what's missing in our mental model here? Like again, theory is like do win rate, maximize it, it's the right thing to do, we should do it. The thing that's missing in our mental model is like, maybe it's like hyperparameters. It's like a good guess. But here we're looking at various different hyperparameters, like making these like assumptions on the classifiers, choosing the different link functions, choosing the different amounts of regularization. There's not really any sort of strong relationship to the hyperparameters in terms of what the performance is. There's some relationship. But if you plot it another way, there's a strong relationship with training loss. And you might be like, hey, I thought that like this problem was solved. Like we could set out an optimization problem and then use gradient optimization, and with a big model, these losses would get to a low value. That may be true if you're doing like this like supervised maximum likelihood kind of way. But when you're doing these search-based objectives, they can be quite difficult to get to optimize. If you're curious about it, you can ask me more, but they're basically guess and check algorithms. They're like, if I did happen to sample something that's a good score, I'm going to give it high probability, but the mechanism to sample something that has a good score is really just guessing. And so like the summary of what we see here is like, what we expect is on the left is like, win rate based on the math is the right thing, and we want to like maximize it. In practice, there's going to be a slew of different algorithms just because there's a difference between the theory and what we know how to optimize. And we kind of need more work here on better ways to optimize or better surrogates, where like surrogates are, again, think about like something you'd find in an old textbook of like, hey, here's something I would like to do. Here's a surrogate that's easier to optimize. Convex surrogates are the place that comes to mind for me. So I'm going to tell you about one last thing, which is about the promise of generative models in healthcare. And this is something that like I've talked about a little bit before here. First, like if you want to think about a generative model, the only thing that you ever get from your problem is the data. So then one set of people would say like, what you should do is you should learn that data distribution, and any subsequent problem you want to solve should just be computed from your estimates of that data distribution. And then that's really like what people do when they train like, a really huge model. They're like, I'm going to fit the internet scale data, and then that is all I can get from that. And then I'm going to try to like tilt it, fine tune it, steer it, and get it to where I need to go. And sometimes you'll do it conditional on queries. Healthcare data is like a sequence. I should say like thinking about health record data here. And it's a sequence of irregularly spaced times and events. And if you see this sequence, you're like, okay, I know that like language is a sequence, and so maybe I could adapt like the technology that people use in building a language model to build a model of this sequence. And so you could say like to build like an event time, event given history distribution, I could just do it with a transformer. And it's a good idea. And what might you be able to do with this? You could do detection. You could say like, does somebody have like a condition right now? You could try to predict something far into the future. You could also maybe like try to guess and check what an action would do. You could say like, oh, let me substitute in an action and say like, hey, what happens if I give cholesterol medications at a higher dose? What happens if I start medication a year earlier? And try to simulate with this model forward to see what would happen. The idea being like what people care about a lot are taking different actions for people to improve the course of their care. And so we could play around with this. Like we could just do this directly as an example. Here I have two examples. I might change what the events are in the description, where the event on the left, I'm going to call a vision check now. The event on the right is maybe getting your cholesterol checked. And if you built this next token model, like what you would get when you expand it out would be a distribution over times and events. And that's this probability table that sums to 1. Here I have 3 different times and I have 2 different events. So there's 6 rows in this probability table. And what I'm interested in is like an intervention on a vision check. So like this black bag, I want it to only happen at 2 weeks. Okay, so we can think about how we might do that. One thing you could do is just say, well, I'm going to take the vision checks that are less than 2 weeks, so these 2 rows, I'm going to zero out their probabilities. If I zero out their probabilities and I renormalize this distribution, these numbers will go up, right? Because I'm dividing by a number that's less than 1. When I divide by a number that's less than 1, these numbers are going to get bigger. And so somehow I'm changing the probabilities of other events. Maybe that's not so good if I'm doing that at earlier times. I could then say maybe that's actually really silly. Maybe what I should do instead is I should only look at these like black bag times. I should set this number to 0, set this number to 0, and then just renormalize it within these 3 numbers. So this number would become like 0.45. And you may see like, oh, that's fine, because I'm not changing the distribution of the other event. But let's like think about this conceptually for a second. Like imagine like, the little time series that I'm after is, this black bag is vaccination, and I'm looking at really young kids. So if I look at really young kids, the next event is going to be vaccination with some high probability, right? Because like kids get a whole bunch of vaccinations in young age. Now let's say that like my intervention is going to be, I don't want to vaccinate kids anymore. I just want to vaccinate them at 20 years old. So if I tell you like the next event has a probability of 0.9 of being a vaccination, then if I then make the intervention, I shift all the probability mass later, I'm going to say that the next event has a probability of 0.9 of being at age 20. And this seems like a funny thing to do, right? Because like I wanted to just intervene on vaccinations. I didn't want to say that this person with probability 0.9 is going to have nothing happen to them until age 20. Right? And so it's not the right intervention in the same way. It's like it feels wrong to us, and it's hard to pin down maybe what we need. And what we really want is we want the rest to stay the same, given some history. Like we want like, hey, how are you going to get like your like annual health checkups to be the same, given the history that the patient has. And so like how do we do this? It seems a little bit hard when we have this setup of a joint distribution. So there is an answer. Again, like, statisticians thought of this answer over the last, at least for interventions, the last 15 years, but maybe the last 50 years when you think about it in terms of these processes. And then the way that they do it is with these things called intensities. So intensities represent like the rates of events happening. And they relate to the hazard representation of a distribution, where the hazard of a distribution is like the density condition on it happening after a certain time. So it's like, what's the instantaneous rate that the event is going to happen right now? But what you need to keep in mind for this discussion is that like intensities of different events sum. And then when you see the sum, you're going to get like, oh, maybe there's an idea. If like I zero out the intensities for event 1, the way that event 0 is going to evolve is going to look the same. Like it's going to have the same underlying rates. And so this definition is like the rates of other events are only changing when the history changes. It's kind of what we want. But if we go back and we look at like what the next token prediction model is giving us, it's a joint distribution over times and events. Right? If we have this joint distribution over times and events, where are the intensities? Intensities looked like there was some like probability divided by like a survival function or 1 minus a CDF. It's not like explicit here. And then like if this is in continuous time, the problem becomes even worse. So there are no model parameters or model outputs that specifically correspond to the things that you want to make interventions on. And so this is kind of where we're at this point. On one hand, like direct next token generative models are super cool because like we can just use all this technology there and we can predict the next time an event. But they don't let us like make interventions in a way that feels reasonable to us. Like we're doing things like saying like, hey, if we change vaccination to 20, everything happens when you're at 20. Intensities give you an answer, like it feels right. Like in being like, hey, I'm not going to change the instantaneous rates of these events, given that the history of the patient remains the same. But you require specialized models. It's not a next token thing. And you also require specialized techniques, like sampling from an intensity. Like, if I were to ask people to raise their hands, I'm guessing, not even me would raise my hand on like how you would do that exactly. But there's a new way to kind of do this. And we're going to actually define something called a competing event model. A competing event model is just going to model the time for each of the kinds of different events given a history, assuming that nothing else happens before it. So you can imagine like there are these little like races that are going on and like, hey, what's the next time that you have a vision check? What's the next time you have a cholesterol one? And then you get samples sometimes. And the thing that's the minimum is actually going to be what happens. And this distribution has a corresponding intensity. And this intensity relates to the intensity where we can do the interventions. The intensity of this distribution is the intensity we care about with the extra fact that nothing has happened in a time interval. And in this way, interventions are easy because if we intervene on this distribution, we're only messing around with the intensity that we care about, which was what our goal was. The other property of this is it's actually a next token model, meaning that like here you're asking to predict times for the k possible events. And so it really is a k next token model where given the history summarized in some way, actually sample each of the k times, pick the minimum, it's a next token prediction. You might say that, hey, maybe that's really expensive. You might be like, oh yeah, that's like hard to do. But if you think about how these probabilities are computed in general, they're going to be like order the number of events anyway. So we're not like changing the complexity more by sampling. And this is really the best of both worlds. You can get like easy interventions, but you can do it with next token generative models. So you can make use of all the infrastructure that people have built, training transformers, scaling them, it all comes into play here. And you can train these with maximum likelihood. If you want to know what the likelihood looks like, just ask me. But it relates to stuff from competing risks and survival analysis. You need a survival function or a CDF. And again, if you want to see now what this looks like pictorially, we could take our trained competing event model, which would give us like, these distributions for each of the two events that correspond to like the probabilities, like, if nothing else happens in between. And if we want to make an intervention, it's going to be as easy as zeroing out the probabilities for 1 hour and 1 week for the thing that we're intervening on. And now we have a new competing event model that we can just sample from. And if we want to see what happens, we're just going to sample from it. And under some heavy conditions, this will be sort of the distribution of what would happen under an intervention. It's straightforward. So I'm going to summarize everything I talked about because it was a lot. There were 3 different pieces. The first piece is really like if you take algorithms from probabilistic inference and then use them to sample in different ways from these big generative models. So we used sequential Monte Carlo with these potentials. You can get better results, like you saw in like the 3D structure for the biomolecular complexes. And you can also get better results with less compute, like we saw in the image, text-to-image modeling. For preference learning, win rate is all that matters. Like it really is the basis of preference learning, and you can prove that, which is what we did. But different methods are sort of trading off fidelity to the actual goal of maximizing the win rate with the ease of optimization. Something like supervised fine-tuning with maximize the likelihood is the easiest to optimize, but it gives you sort of maybe the least sort of like, preference optimization, whereas just like maximizing the preferences would be the most direct thing, but it's super hard to do. And we really need more work on optimization and surrogates. I think that would help a lot if we could sort of figure out how to take the thing that we really care about and answer it well, like meaning that instead of answering the wrong question well, try to figure out a better answer to the right question. And the last bit we saw is that for competing event models, like we really want to use like the infrastructure that's already there on healthcare data. You can use the libraries that are present to just train on, say, something like an EHR. And we have questions in healthcare about interventions. And there's not really a way to do that. But competing event models really make it easy to take a next token generative model and do interventions on specific events. And this is all relatively recent work. 2 of these things were at ICML this year. The last bit is at a workshop at ICML. It's done by lots of people. I'm highlighting Rajesh Singhal, who's a student of mine, Yoav Wald, who's in the audience back there, who's a faculty fellow who works with me, who will be a professor at Technion, and Lily Zhang, who just finished up her PhD. And I'll take any questions now.